Imagine stepping into a sleek supersuit, pushing a little button on your glove, and just instantly shrinking to the size of an ant.
Yeah, the classic comic book dream. You
Right.
become a superhero, you ride flying insects, punch bad guys, save the world.
Exactly.
Right.
But in real life,
Yeah.
your lungs would instantly suffocate on oxygen molecules that are, suddenly way too large for your tiny body to process.
Oh, and your eyes go completely blind.
Right. Because visible light waves just bypass your microscopic pupils
Yeah.
and the sheer concentrated density of your human mass. It basically turns you into a human bullet that would crush whatever you tried to stand on.
It's really the ultimate collision between blockbuster movie magic and just completely unforgiving real-world physics. I mean, we're so used to suspending our disbelief when someone shoots lasers from their eyes, for sure. But when a story tries to ground its superpowers in actual scientific concepts like atomic relative distance or quantum entanglement or, entomology, it practically begs us to pull out a microscope and see if the math actually holds up.
Well, welcome to today's deep dive. We are putting the Marvel Cinematic Universe under the lens for you today, specifically the world of Ant-Man. Our mission is to explore the real-world science behind these films and figure out if, his incredible abilities could actually exist in our reality.
It's a huge topic.
It is. And to do this, we've pulled together an incredibly diverse stack of sources for you. We're looking at deep dives into theoretical physics from Science ABC, Space.com, and Looper. Plus, we have biological and entomological breakdowns from the educational supplier EduLab, the extensive comic history from Wikipedia, and this is my favorite, a really illuminating NBC News interview with Caltech quantum physicist Spiridon Mikalakis.
Right, and he actually consulted on the Marvel films, which makes his insights so valuable. It's a phenomenal stack of research because it forces us to cross-reference multiple scientific disciplines.
We really have to jump from quantum mechanics to biology to structural engineering just to understand a single scene of a guy running across a table.
Yeah, it's wild.
So, to set the stage for you, the legacy of Ant-Man is pretty expansive. According to the comic history on Wikipedia, quite a few people have worn the suit over the years. You've got the original inventor, Hank Pym. You have the modern movie protagonist, Scott Lang. There's an opportunistic agent named Eric O'Grady. And the lore even stretches to a time-traveling character named Zane Asgar from the year 2549.
I always forget about Zane.
Right. But regardless of who is wearing the helmet or what year they come from, the core mechanic that makes the entire premise function is the Pym particle. Okay, let's unpack this. How exactly is this shrinking supposed to work in the first place?
So the films and comics explain that Pym particles shrink an object by compressing the empty space between atoms.
Go away.
And crucially, it does this without removing any of the object's actual mass. Now, on paper, if you consult a physicist like Jed McCusker, he's from Wake Forest University, he points out that atoms actually are mostly empty space.
Which sounds crazy, but it's true.
Exactly. Almost all of an atom's mass is concentrated in a remarkably tiny nucleus, which is surrounded by this vast, buzzing electron cloud. So the theoretical premise relies on the idea that there's, plenty of room within that atomic structure to just squeeze everything closer together.
I have to say, I have a hard time wrapping my head around that empty space concept. Because when we use words like empty, it makes an atom sound like a sponge that you can just wring out if you squeeze hard enough.
Yeah, that's a common misconception.
But an atom's empty space isn't just air you can compress. I always picture it more like the structural integrity of a solid bowling ball. It might be mathematically empty space inside, but it's held together by intense physical bonds. You can't just squish a bowling ball down to the size of a marble.
I see where you're going with the bowling ball idea, but it's a bowling ball resists being squished because of structural chemical bonds between its molecules.
Right.
An atom's resistance is actually much weirder than that.
Weirder how?
It isn't a structural barrier at all. It's a fundamental quantum rule. The reality check here comes down to the Pauli exclusion principle.
Oh, right.
Yeah, in quantum mechanics, electrons absolutely refuse to share the same quantum state. Think of it like a cosmic game of musical chairs where the rules of the universe physically forbid two people from trying to sit in the exact same chair.
So if you try to force them into a smaller volume, they rebel.
Ferociously. This pushback is called electron degeneracy pressure. When you try to compress that empty space, the electrons exert an outward force that is almost incomprehensibly strong. To give you a sense of scale, electron degeneracy pressure is the exact same mechanism that prevents a white dwarf star from collapsing in on itself under its own immense gravity.
Wait, really? A dying star?
Yes.
So to shrink a single atom, Hank Pym isn't just deflating a microscopic balloon. He has to invent a particle that can casually overpower the mechanical forces of a dying star.
Exactly. And he has to do it for every single one of the 7 octillion atoms in the human body simultaneously without blowing himself up.
That is wow. Okay, well, let's pretend he actually pulled that off. Let's just assume the Pym particles successfully bypass the Pauli exclusion principle.
Generous of us, but okay.
Very generous.
Yeah.
If we look at the biological side of things, pulling from our EduLab and Space.com sources, shrinking a human body introduces a terrifying cascade of side effects.
Yeah. The biology is really where the fantasy starts to unravel. The moment you shrink, your body's systems are suddenly entirely out of scale with the environment they evolved to interact with.
Let's start with just the most basic human function, right? Taking a breath.
Okay.
At the size of an ant, your lungs are microscopic. But the oxygen molecules in the air around you haven't shrunk at all. Those molecules are now proportionally massive compared to the tiny alveoli in your lungs.
Which is a huge problem for gas exchange.
Exactly. Trying to breathe normal air at that scale would mean you simply couldn't process enough oxygen molecules per breath. It would feel exactly like suffocating at the peak of Mount Everest, just gasping for thin air.
Yeah, because the surface area of your cellular receptors would be too small to catch the oxygen passing by. And oxygen isn't the only environmental factor that suddenly stops working for you. The physics of light become a massive problem, too.
Your vision would be completely ruined.
Oh, absolutely.
Because visible light exists in specific wavelengths, roughly between 400 and 700 nanometers.
Right.
If you shrink down to half an inch tall, your pupils become smaller than the actual wavelength of the light you're trying to see.
Right, so the light can't even get in properly.
The light waves wouldn't enter your eye cleanly at all. They would diffract and scatter as they tried to pass through that tiny aperture. Your vision would be a hopelessly blurry, washed-out mess.
Yeah.
You would essentially be blind unless you managed to rapidly evolve the specialized compound eyes of an insect.
Which, let's be honest, would look terrible on a movie poster.
Terrible. Not a good look for Paul Rudd.
Not at all. And the acoustic shifts are just as dramatic. If you are suffocating and blind, you can't even call out for help because the mechanics of your vocal cords have fundamentally changed.
Right, because the pitch of your voice is dictated by the length and tension of your vocal cords.
Yes. As you shrink, those cords become incredibly short. And shorter cords vibrate much, much faster. The sources estimate that at ant size, your vocal cords would be vibrating at a frequency of around 3,500 hertz and potentially pushing all the way up to 12 to 26 kilohertz.
And human hearing generally tops out around 20 kilohertz, right?
Yeah, and that's for young people with perfect hearing.
Meaning your shouts for help would be pushed completely outside the range of human perception.
Yeah.
You'd be producing these ultra-high frequency, imperceptible peeps and squeaks. Or, best case scenario, you'd sound like a chipmunk who just inhaled a tank of helium.
And while you were dealing with all of this suffocating, blind squeaking, your body is also rapidly freezing to death.
Oh, because of the heat loss.
Exactly. It comes down to the relationship between surface area and volume. As you get smaller, your volume decreases much faster than your surface area. You're suddenly exposing a massive amount of surface area to the cold air relative to the tiny amount of heat-generating volume inside your body.
So your metabolism would just freak out.
To counteract that rapid heat loss, your metabolic rate would have to skyrocket. You would need to be consuming high-calorie food constantly, like a shrew or a hummingbird, just to maintain your core temperature.
The biological reality is incredibly grim. But since this is a superhero narrative, we have to assume the Ant-Man suit is a technological marvel that magically regulates his oxygen, corrects the light diffraction, modulates his voice, and somehow keeps him warm.
It's doing a lot of heavy lifting, that suit.
It really is. But even if we grant the suit those miracles, we still have to look at the macro physics. How does a shrunken human actually interact with the physical world?
This is where we run into the paradox of mass. The films establish a very specific rule early on. When Scott Lang shrinks, he retains his full original human mass. He still weighs about 90 kilograms, or roughly 200 pounds.
Right, and the movie uses this to explain his combat abilities. A punch from Ant-Man hits with the force of a bullet, because all of that 200-pound momentum is concentrated into a fist that is only a fraction of a millimeter wide.
Which makes for incredible action sequences. But as you were saying, retaining that mass creates major issues when you look at how he moves around. Now, you might be picturing Scott Lang lightly dropping onto a record player or riding around on the back of his flying ant. But think about the math we just did.
Oh, no.
If he still weighs 200 pounds, that ant isn't taking flight. It's getting crushed instantly. What's fascinating here is how the films immediately break their own fundamental rule for the sake of visual storytelling.
They really do.
If you pack 90 kilograms of mass into an object the size of an insect, you are creating a density that defies normal material physics.
It's almost like you'd become a walking black hole.
Well, not quite a black hole. You wouldn't be warping space-time, but you would be incredibly dense.
Yeah.
Far denser than osmium or a solid tungsten needle. If you stood on a normal surface, all 200 pounds of your weight would be focused down into the microscopic surface area of your tiny boots.
So you couldn't run across a villain's gun barrel.
No, you would puncture straight through it like a hydraulic press. And you certainly couldn't be flicked harmlessly across a room by a bad guy, because trying to flick a 200-pound concentrated weight would just shatter the bad guy's finger.
That mass paradox gets pushed to absolute absurdity in the sequel, too.
Oh, the building.
Yes. Dr. Pym shrinks a fully equipped 10-story laboratory building down into a little rollable suitcase with an extendable handle, and then they casually roll it into a regular commercial van and drive it around San Francisco.
Which is completely impossible. A 10-story building made of concrete, steel, and heavy lab equipment weighs tens of thousands of tons. If the mass is retained, shrinking the volume doesn't change the weight at all.
So that van is toast.
Dragging a 20,000-ton suitcase into the back of a standard van wouldn't just pop the tires. The concentrated ground pressure would punch a hole straight through the chassis and crush the asphalt beneath it.
Unbelievable.
Moving something with that kind of mass through a city would cause severe traffic-induced vibrations. Every pothole they hit would send shock waves through the ground, easily triggering local seismic activity. The FBI wouldn't even need to look for a van. They just need to track the localized earthquakes.
That is hilarious. So retaining mass is a logistical nightmare. But looking at the calculations from space.com, is there any physical advantage to being that small and that dense? Because the movies show him moving incredibly fast.
The biomechanics there actually do work in his favor, surprisingly. If you have the muscle mass and power output of a full-grown athlete, but you are only half an inch tall, your relative strength is astronomical.
Interesting.
Furthermore, you have virtually zero aerodynamic drag relative to your power. Space.com calculated that if you took an Olympic sprinter like Usain Bolt and shrank him down to ant size while maintaining his power output, his stride frequency and launch force would allow him to run at speeds of up to 540 miles per hour.
540. That is nearly 80% of the speed of sound. He would literally be a blur.
Yeah, he'd be unstoppable.
But of course, the suit doesn't just shrink things. The technology goes in reverse. Antman famously becomes Giant Man, reaching heights of up to 65 feet tall. And growing massive introduces a completely different, totally merciless physical reality, right? Galileo's square cube law.
Yes, Galileo formulated this centuries ago, and it remains the ultimate reality check for any giant monster or superhero. The square cube law describes a geometric principle as an object scales up in size, its volume, which dictates its weight, grows vastly faster than its surface area, which dictates the strength of its structural supports.
So let's break down the actual math for a 65-foot Scott Lang. If he grows by roughly a factor of 10, how does that disparity play out in his body?
Well, the strength of human bones and muscles is proportional to their cross-sectional surface area. So if he grows by a factor of 10, his strength increases by 10 squared. He becomes 100 times stronger.
Okay, that sounds great so far.
However, his total mass and volume increase by 10 cubed. He becomes 1,000 times heavier.
Oh, so his bones are 100 times stronger, but they are suddenly being asked to support 1,000 times more weight.
Exactly. The human skeletal system simply cannot support that mathematical ratio. The cross-sectional area of his femur would not be wide enough to withstand the sheer tonnage of his upper body. The moment he took a step forward at 65 feet tall, the compressive force would turn his leg bones into powder.
Ouch.
Yeah, he would instantly collapse under his own colossal weight.
If the physics of the macro world are that hostile to him, I mean, if the square cube law crushes him when he's big, and the density paradox causes local earthquakes when he's small, it makes perfect sense why the narrative of the films pushes Scott past physical limits entirely. He doesn't just stay ant-sized, he goes subatomic. He shrinks down into the quantum realm.
It is a brilliant narrative pivot, really. When classical physics becomes a trap, you just move the story into a space governed by quantum mechanics, where the rules of reality are fundamentally different.
And what I love is that the writers weren't just throwing darts at a board of sci-fi buzzwords. They brought in Caltech physicist Spiridon Mikalakis to consult. He's actually the one who coined the specific term quantum realm for the Marvel Cinematic Universe.
I didn't know he coined it. That's
Yeah.
awesome.
And here's where it gets really interesting. In the third film, there's a sequence where Scott gets trapped in a probability storm. He sees infinite multiplying versions of himself, all making slightly different choices, overlapping each other. It visually feels like a choose-your-own-adventure book where you were reading every possible ending at the exact same time.
That scene is such a fantastic visual metaphor for the real quantum concept of superposition.
How so?
In quantum mechanics, particles don't have to exist in just one defined state. Until they are measured or observed, they can exist in multiple possible states simultaneously. It is the famous Schrodinger's cat thought experiment brought to life on an IMAX screen.
Where the cat in the box is both alive and dead simultaneously as a probability wave.
Exactly. In the quantum realm, Scott's probability wave hasn't collapsed. He is experiencing every possible version of Scott all at once.
It's completely mind-bending. And they layer even more quantum theory into the plot with Janet Van Dyne. She is trapped subatomically in the quantum realm, yet she manages to send communications back to her family in our macro reality. How do you explain sending a message across dimensions?
They lean on a very real, verified phenomenon called quantum entanglement. Albert Einstein famously scoffed at this idea. He called it spooky action at a distance, but it works.
It's proven right.
Yes, two subatomic particles can become inextricably linked, regardless of the physical space between them. If you measure or change the spin state of one particle, the entangled partner instantly reflects a corresponding change. It doesn't matter if they are separated by a millimeter or placed on opposite ends of the universe, the connection is instantaneous.
That's incredible.
Scientists definitively proved this with Bell test experiments culminating around 2015. So using entanglement as an interdimensional Morse code is a highly clever application of real physics.
The attention to detail extends to the visual design, too. When Scott first starts shrinking past the microscopic level, he encounters dust mites floating in the air. The design of those mites looks exactly like the terrifying, jagged imagery you see captured by actual electron microscopes.
Yeah, they nailed the look.
And a bit further down, they show tardigrades, microscopic water bears floating past him. They absolutely nailed the biological scale there, since real tardigrades measure about 0.4 millimeters in size.
The microzoology is spot on. But we do need to draw a firm line at how the films eventually treat the quantum realm as a physical location.
Right.
Physicist Chris Ferry points out a major public misconception here. The quantum realm is not a hidden geographical dimension underneath our own, like a microscopic Narnia. You can't travel there in a ship and walk around on quantum dirt. It is simply a different mathematical framework for understanding the fundamental building blocks of our existing reality.
And from a pure physics standpoint, trying to exist as a discrete object down there presents a ticking clock. Science ABC highlights a terrifying reality of scale. If Scott shrank down so small that he reached the size of a free neutron, he would become subject to the physical lifespan of a free neutron.
Which is not long at all.
Right.
Inside the nucleus of an atom, bound by the strong nuclear force, a neutron is incredibly stable. But once the neutron is free-floating, it is highly unstable. The weak nuclear force takes over, causing one of its down quarks to spontaneously flip into an up quark.
And that's called beta minus decay, right?
Exactly. Within about 15 minutes, that free neutron will completely disintegrate, transforming into a proton, an electron, and an antineutrino. If Scott's mass was compressed to that scale, his cellular structure would undergo catastrophic beta decay. He would literally evaporate into subatomic shrapnel.
Wow. We have spent so much time exploring the lethal mechanics of the quantum world, but we absolutely cannot do a deep dive on Antman without examining his namesakes. We have to look at the macrobiology of the ants he works alongside.
Oh, for sure. The entomology is a fantastic mix of rigorous fact and just wild fiction. The films feature several distinct species of ants, and how they behave tells us a lot about real insect biology.
Let's run through them. Think about the carpenter ants. In the movies, Scott uses them as his personal air force. They fly him around on covert missions. But if I remember correctly from the EduLab sources, carpenter ants don't just cruise around the sky all day.
No, they don't. Carpenter ants are indeed powerful lifters. They're capable of hollowing out wood for nests, but depicting them with permanent wings is a massive stretch.
When do they have wings, then?
In nature, ant colonies produce winged variations, which are called alates, only during very specific brief windows for mating and establishing entirely new colonies. They shed those wings shortly after, so relying on them as a permanent 2047 taxi service just doesn't align with their actual life cycle.
What about the bullet ants? Hank Pym uses them as his shock troops, the heavy hitters that swarm the bad guys.
That is painfully accurate. Bullet ants are infamous in entomology. They rank at the absolute top, a level 4 on the Schmidt pain index.
Yikes.
Yeah, their sting delivers a neurotoxin called poneurotoxin that directly affects the central nervous system. It causes violent muscle contractions and a burning agony that lasts for up to 24 hours.
24 hours.
Yes. The creator of the index described the pain as pure, intense, brilliant pain that shuts down all illusions of normal life. Weaponizing them is a terrifyingly logical choice.
Okay, note to self, avoid bullet ants. We also see him utilize fire ants, having them link their bodies together to form bridges and little rafts to carry him across water pipes.
Completely true to life, fire ants exhibit an astonishing form of swarm intelligence. When faced with floods, they actually interlock their mandibles and legs to create waterproof rafts out of their own bodies, trapping air bubbles to stay afloat.
That is so cool. And the crazy ants. They are deployed to infiltrate the villain servers and short out the electrical circuits.
Also a very real phenomenon. Tawny crazy ants are notoriously attracted to electrical fields. They will swarm into junction boxes and computers, and when they get shocked, they release an alarm pheromone that attracts even more ants. They accumulate until their dead bodies completely fry the electrical wiring.
So what does this all mean? The behaviors of the specific ant species are surprisingly well researched, but the way Hank Pym actually commands them is through an earpiece that supposedly transmits electromagnetic waves to stimulate their olfactory nerves. Let's apply some scrutiny there. Is there any reality to electromagnetic insect mind control?
That is where we cross firmly back into science fiction. It's entirely true that ants communicate highly complex information from food trails to colony defense through their olfactory nerves by smelling chemical trails called pheromones.
Right, chemicals.
Exactly. But a chemical pheromone is a physical molecule. You cannot mimic a physical molecule using an electromagnetic radio wave. That is the equivalent of trying to bake a cake by shouting a recipe at an empty oven.
That's a great analogy.
The receptor needs the physical chemical to trigger the response.
If we connect this to the bigger picture, though, there is one massive, glaring entomological error that runs through the entire Ant-Man franchise, isn't there?
The biggest oversight of all, yes. The worker ants. The soldiers, the bridge builders, the ones flying Scott around in the real world, they are exclusively female.
Every single one of them.
Every one of them. In ant colonies, the males essentially exist solely to mate during those brief flying windows, and then they die. The entire functioning workforce and military of a colony is female. So when Scott names his trusty flying steed Anthony, he really should have named her Antoinette.
Antoinette. That is incredible. The franchise also plays with ant evolution in the newest movie, where a colony falls into the quantum realm, experiences severe time dilation, and rapidly evolves into a highly advanced, super-intelligent socialist society.
Which is a brilliant sci-fi trope. Because ants are naturally eusocial, meaning they work collectively for the survival of the colony above the individual, a technologically advanced socialist society is the logical endpoint of their evolution.
So it makes sense on paper.
The issue is the timeline. The film suggests they achieved this over a few thousand years of time dilation. Realistically, evolving from a standard insect into a civilization with architecture and metallurgy requires millions of years of selective evolutionary pressure, not just a couple of millennia.
That makes sense. And speaking of the physical toll of sci-fi concepts, we also have to mention the villain Ghost from the second movie. Her powers are based on a condition they call molecular disequilibrium, which allows her to use quantum phasing to walk through solid walls.
Yeah, they are heavily borrowing from the real physics term quantum tunneling.
What's that?
Quantum tunneling is a verified phenomenon where subatomic particles, behaving as probability waves, can occasionally pass through a solid potential energy barrier that they shouldn't mathematically have the energy to cross. But applying that to human biology via molecular disequilibrium is purely fabricated.
Because we're not subatomic particles.
Right. The structural integrity of human biology relies on stable chemical bonds. If every molecule in your body was constantly losing its bonds, phasing apart, and trying to stitch itself back together, you wouldn't gain the ability to walk through walls. Your proteins would instantly unravel, and you would experience immediate catastrophic cellular death.
So if we look at the grand summary of our deep dive, putting on the Ant-Man suit means the physics of mass would turn you into an impossibly dense, road-crushing weight. The square cube law would snap your giant bones like twigs, your vocal cords would shriek in ultrasonic frequencies, and quantum phasing would vaporize your cells long before you could fight crime.
The scientific hurdles are entirely fatal, but credit must be given where it's due. Marvel took incredibly dense theoretical concepts like quantum entanglement, superposition, the Pauli exclusion principle, and accurate microzoology, and seamlessly wove them into a blockbuster popcorn movie.
And that is exactly why we do these deep dives for you. Because why should any of this matter to you? Superhero movies aren't just idle fantasy. They are brilliant Trojan horses for curiosity. Picking apart the fiction, asking why a 200-pound man can't ride a flying ant, or why he can't breathe when he shrinks, is a fantastic, engaging way to stumble into learning about the actual mind-blowing rules of our universe. You might buy a ticket just to see Paul Rudd, but you leave the theater trying to understand electron degeneracy pressure.
It's the best kind of learning because it begins with a genuine question.
Absolutely. To leave you with one final provocative thought to mull over. Remember Dr. Spiridon Mikalakis, the quantum physicist who consulted in the films? In his interviews, he pointed out that while Pym particles are entirely fake, scientists actually can shrink matter in the real world.
Yes, utilizing massive particle accelerators like cyclotrons.
Exactly. Using these accelerators,
Yeah.
physicists can create something called muonic matter. An atom size is dictated by the orbit of its electrons. But scientists can completely replace an atom's electrons with exotic particles called muons.
Right.
A muon has the exact same charge as an electron, but it is 200 times heavier. Because it possesses so much more mass, the electromagnetic pull from the atom's nucleus reels the muon into an orbit that is 200 times tighter in order to maintain angular momentum. They literally create atoms that are 200 times smaller than normal.
It's amazing stuff.
So imagine this for a second.
Yeah.
What if the true key to shrinking isn't trying to compress the empty space in your atoms, but entirely replacing the fundamental building blocks of your body with heavier exotic particles? And what would it feel like to exist as a hyperdense, muonic human for the microscopic fraction of a second before you decayed back into normal matter? Something for you to think about next time you see an ant on the sidewalk.